Alright, so what we're learning today is the rational and imaginary root theorems. And what we're going to start off with is being able to rewrite a polynomial in factored form. So when we write our quadratics in factored form, it would just be like, oh, hold on. So we had factored form. And a quadratic in factored form would just be something like x minus 2 times x plus 3. And if I were to multiply those out, I would get a quadratic. And if I had set this equal to 0, that would tell me that my roots of this quadratic are positive 2 and negative 3. Because if x minus 2 is 0, x is 2. If x plus 3 is 0, x is negative 3. So that would be the factored form of a quadratic. So factored form of a polynomial, polynomials have more than two roots because, well, a quadratic is just a polynomial with two roots. So, let's see, I am going to use, we had this polynomial that we did on the packet last week. It was the example one. It was x to the third plus x squared minus 8x minus 12. And I'm trying to think. I believe we said the roots were negative 2, negative 2, and positive 3, unless it was positive 2 and negative 3. But I think it was negative 2, positive 3. Okay, I think we said the roots of this. So the roots were negative 2, negative 2, and positive 3. So what this means is if we have x equals negative 2, and x equals negative 2, and x equals 3. So now we want to get all of these equal to 0, because the way we find the zeros is getting them equal to 0. So let's see, if x equals negative 2, first thing I'm going to do is add 2 to both sides. So x plus 2 equals 0, and there is one of my factors. And here we have x equals negative 2, add 2, so x plus 2 equals 0. And finally, we have x equals 3, subtract 3 from both sides, x minus 3 equals 0. Which means, since I have x plus 2, x plus 2, x minus 3, the factored form of x to the third plus x squared minus 8x minus 12 was going to be x plus 2 times x plus 2 times x minus 3. And if I multiply these three together, I'll get back to this up here. And another way to write this would be x plus 2 squared, since there's two of them, x minus 3. So if I multiply, so either of these are factored form of the polynomial. So what we're going to do now is, the other case I want to show you guys is if there are fraction roots. So let me find another one from the packet. So here is the other example I'll do was number 4 in the packet. It was 2x to the third minus x squared minus 13x minus 6. And we were finding the zeros of that and whatnot. So to write this one in factored form, let's see, the roots were, let me actually check what the roots were real quick. So the roots were negative 2, negative 1/2, and 3. So negative 2, negative 1/2, and 3. So actually, two of those roots are the same. It's just instead of one of the negative 2's, we have a negative 1/2 instead. So we have x equals negative 2, x equals negative 1/2, and x equals 3. So what we're going to do with this we have x equals negative 2, so add 2 to both sides. So we have x plus 2 equals 0. We'll come back to that one in the middle. And if x equals 3, subtract 3 from both sides. X minus 3 equals 0. So we want to set everything equals 0. Now we have this x equals negative 1/2. Instead of just adding 1/2 to both sides, I want to get rid of the fraction altogether. So the first thing I want to do is actually multiply both sides by 2. Multiply both sides by that denominator there. So that's going to give me 2x equals negative 1. And then to get it equal to 0, I'm going to add that 1 to both sides. So 2x plus 1 equals 0. And now our factors are x plus 2, 2x plus 1, and x minus 3, which means the factored form of this is going to be x plus 2 times 2x plus 1 times x minus 3. And real quickly, I will show you guys how to multiply this together. So let's see. I'm just going to, like with the regular quadratic, I'm going to multiply the first two together. So I have x plus 2 times 2x plus 1. So let's see. X plus 2 times 2x plus 1. I'm just going to multiply two factors at a time, excuse me. All right, and I'm going to FOIL this. So x times 2x is 2x squared, 2x squared. X times 1 is x. 2 times 2x is 4x. And wait, yeah, 2 times 2x, and then 2 times 1. 2 times 1 is 2. So when I combine like terms, I get 2x squared plus 5x plus 2. But I still have that other factor of x minus 3. So I'm taking this and multiplying it by x minus 3. So first thing I'll do, take the 2x squared, distribute it to both inside there. So 2x squared times x is going to be 2x to the third. 2x squared times negative 3 is going to be minus 6x squared. And then I have 5x times x. Well, 5x times x is going to be 5x squared. And then I have 5x times negative 3, which is negative 15x. And then I have 2 times x. 2 times x is going to be 2x. And then I have 2 times negative 3. 2 times negative 3 is negative 6. So now I have this big thing, and all I have to do is combine like terms, just like I did previously, and that is going to get me 2x to the third, and then I have minus 6x squared plus 5x squared, which is going to be minus x squared. And then I have a minus 15x plus 2x is going to be minus 13x. And then I have a minus 6. So I have 2x to the third, or minus x squared, minus 13x minus 6, which is exactly what we started with. So that's how you get from factored form back into the standard form. Okay, so with that being said, once you find the zeros, you can rewrite a polynomial in factored form. So what we're going to be working with today is irrational and imaginary roots of polynomials. So let's see, I have this first polynomial, and this part isn't really going to rely on what we just learned, but it is kind of important. So I have this polynomial f of x equals x squared plus 6x minus 38. It is asking me to state the number of complex zeros and the possible number of real and imaginary zeros for each function. Okay, so just 1 second. Oh yeah, okay. So the number of complex zeros, we know how to do this. All it's doing is it just put the word complex there. It's just saying, how many zeros are there? What are the number of zeros? So the number of zeros, So zeros, well, there's two of them. We learned this when we did the packet. It would just be the number of the exponent. So the possible number of real and imaginary zeros. So it's not asking what are the zeros. It's asking what are the possible, the possible numbers of them. So for real zeros, I could have two real zeros, because what if I have, hold on, okay, sorry, let me restart. So I said there are two zeros total. Both of them could be real zeros. So we'll say RZ could be 2, and I'll come back to that in a second. But then there's imaginary zeros, IZ. So the imaginary zeros, what if both those zeros are imaginary? It's 2. And this is where things get a little bit difficult, a little bit trickier, because we're saying that the imaginary zeros, there could be 2. The real zeros, there could be 2, but there's only 2 total. So what if I have one imaginary and one real? Well, I can't actually have one imaginary and one real, because if you remember from last unit, the imaginary numbers always come in pairs with their complex conjugate. So for imaginary zeros, the number of imaginary zeros right here, thought that highlighter would be bigger, but the number of imaginary zeros is always even numbers. So you can never have 3 imaginary zeros because they have to come in pairs. You can never have 1 imaginary zero because they have to come in pairs. So for imaginary zeros, I could either have 2 or I could have none. Those are my only options. I can't have more. I mean, I could have 4, but there's only 2 zeros total. So for the real zeros, since our imaginary zeros, there's either 2 or 0. Well, if there's 2 imaginary zeros, that means none of the zeros are real. So if there's 0 imaginary zeros, so if there's 2 imaginary zeros, that means none of them are real. If there's 0 imaginary zeros, that means 2 of them are real. And there's only 2 total. So that's why the numbers are 2 or 0 and 2 or 0 for both of them. So I want to try, and that's all we have to have. Like, that's the possible numbers. We don't have to figure out how many there actually are. We just have to figure out, there's possibly like this many. So looking at number 3 now, this has degree of 5, which means the number of zeros is 5. There are 5 total. So, well, I'll start with imaginary zeros actually. So imaginary zeros. So there are 5 of them, and I know they come in pairs. So I know that what if all 5 of them are real? That means none of them are imaginary. But if there's one that's imaginary, that means there has to be another one that's imaginary, because they come in pairs. They always come in pairs. So if I could have 0 or 2. And since it goes up to 5, I could also have another pair of imaginary zeros. I could have up to 4 imaginary zeros on this one. 0 or 2 or 4. But I can't have 6 because there's only 5 total. But like I said, they always come in pairs, and it's always even numbers for imaginary zeros. So I'll make a little note. I'll even do it in a different color. We'll say green. Always even. Imaginary zeros, always even. Okay, and then the real zeros. So we said there are 5 zeros total in this polynomial. So if none of them are imaginary, that means that 5 of them are real. If 2 of them are imaginary, well, since there's 5 total and 2 are imaginary, that means the other 3 are real. And if 4 of them are imaginary, that means the other 1 is real. So either way, these numbers, the imaginary plus the real, has to add up to 5 because there's 5 total. And this is all you really have to do for this section here. You have to state the number of imaginary and real zeros, and I believe there's actually a question on the test that's like this. I don't know if I'll actually have you guys taking the test or not. I haven't decided about that yet, but yeah, I'm pretty sure there's one that's like, oh, state the number of zeros and then state the number of real and imaginary zeros. So that's all you're doing for the rest of these problems here. Just remember, imaginary zeros always multiples of 2. The real zeros, it's whatever the zeros are minus the imaginary zeros. So with that being said, we're going to move on to this next section. We have a polynomial function with rational coefficients has the following zeros. Find all the additional zeros. So we have to have a complex conjugate for some of these numbers, for these imaginary numbers. So it's saying that I have a polynomial function. It's not telling me what the polynomial function is, but it's telling me that it has these two zeros, -5 and I. -5 is already a rational number. That's already a real number. I is not a real number. It's not a rational number. It is a rational number, my bad, but it's not real. So I have to include its complex conjugate. So if I have -5 and I, that -5, I don't have to worry about that, but that I do have to worry about that. So I'm going to have -5 I, and the third zero here is going to be -I, because remember, the complex conjugate, it was A plus BI was one of them, and then A minus BI was the complex conjugate. So in this case, we just have I, which is like 0 plus 1I. It's like 0 is A and 1 is B. So then I also have to include 0 minus 1I. And minus 1I, that's just -I. So that means I have to have the complex conjugate of these imaginary numbers. And the same thing is going to apply to irrational numbers. So I will, let's see, what's a good one for me to do? Or not irrational, yeah, irrational numbers, irrational numbers. Let me see this one. I like number 12. Also, when you do this, skip 13 and 14. We don't really care about the multiplicity ones right there. But I'll do number 12. Wait, no, number 12 isn't a good one. That doesn't have any irrational numbers. I'm trying to find a good one. I like 9. Okay. So yeah, 9. So 9, I have -3 plus square root of 5 and -I. So as I just said, if -I is included, I is included, which means that another 0 for this one is going to be I. And the other 0, the same rule applies with these complex conjugates for these irrational numbers. So I have -3 plus square root of 5, which means I also have to have -3 minus square root of 5. And you'll see why this is in the next section. So if I have -I have to have I. If I have -3 plus square root of 5, I have to have -3 minus square root of 5. And once I multiply all these factors together, I will get a polynomial function with rational coefficients that has the following zeros. Okay, so now you'll see that in practice. So, number 15, we have a polynomial function of least degree with integral coefficients has the given zeros. So they're telling you what 3 of the zeros are. Intuitively, you have to know what the other one is. Or there might be more than one extra one. I know that there's one like this on the test, and it's saying polynomial function, least degree, integral coefficients, rational coefficients. Well, integral, you can just assume it's rational. So if I have the square root of 3, that means I also have negative square root of 3. just like I discussed in the section up there. So this means the factors, or the factored form of this polynomial that they're doing in number 15 here, are going to be, well, I have x minus 0, because it's telling me 0 is one of them. And let's see, if 2 is one of my roots, it's just like what I did up at the top. This is why I did what I did up at the top. So I had x minus 2 is one of the roots, because if x equals 2, subtract 2 from both sides, x minus 2 equals 0. Next, I'm going to have x minus square root of 3, and then x plus square root of 3. So these are 4 factors. This is factored form of the polynomial. What I want to do is write it in standard form. So I'm going to multiply 2 factors at a time. I got x minus 0 times x minus 2. X minus 0, I'm just going to go ahead and rewrite that as x times x minus 2, because x minus 0 is just x. Distribute. And now I have x squared minus 2x. All right, and then I have x minus square root of 3 times x plus square root of 3. Let's see, I'm going to do x times x is going to give me x squared. X times the square root of 3 is the square root of 3x. Negative square root of 3 times x is minus square root of 3x. And then the negative square root of 3 times the square root of 3. Well, square root of 3 times square root of 3 is 3. And since it's negative, got negative 3. So I have x squared plus 3x, or plus square root of 3x, minus square root of 3x, minus 3. So now, once I combine like terms, well, square root of 3 minus the square root of 3 is 0. So this is going to give me x squared minus 3. So now I have these 2 factors, x squared minus 3 and x squared minus 2x. And I'm just multiplying them together. So I got x squared minus 2x times x squared minus 3. So x squared times x squared is x to the 4th. X squared times negative 3 is going to be negative 3x squared. Negative 2x times x squared is going to be negative 2x to the 3rd. And negative 2x times negative 3 is going to be 6x, positive 6x. So this, actually, I will switch the order of some things here, just to make it a standard form polynomial. Okay, there. So that is standard form of the polynomial that has the roots 0, 2, square root of 3, and negative square root of 3. And if I were to solve it, I would get 0, 2, square root of 3, negative square root of 3 as my roots. All right, awesome. And you have to include that complex conjugate. Some of these are going to try to throw you off. Like look at number 18 there. They included 3 factors with that I, but one of them already has this complex conjugate because you have 2i and you have negative 2i. We don't got to worry about that. But you do have to have the complex conjugate of this one right here. Let me see. What's a decent one I can do? I think I'll do number 19. That one looks decent. Okay, so we have these 2 numbers, or these 2 roots, and both of them require complex conjugates. So if I have negative 2i, that means I also have to have positive 2i. And if I have 2 plus 2 square roots of 2, that means I also have to have 2 minus 2 square roots of 2. All right, so now let's get into it. when we construct our polynomial in factored form, I'm going to have x plus 2i. And I'm just going to rearrange some factors here, just so things will be easier to multiply together. I'm going to have x minus 2i. And then I'm going to have x minus, parentheses, 2 plus 2 square roots of 2. And then I'm going to have x minus, parentheses, 2 minus 2 square roots of 2. So be very careful with these two factors. They're both x minus, because these are the two zeros that I'm working with. I'm working with this number here and this number here. And back at the top, we did this by subtracting whatever it was from x to get our factor. So that means I do have to have these factors. So let's see. First thing I'm going to multiply together is x plus 2i times x minus 2i. Okay, so let's see. X times x gives me x squared. X times negative 2i is negative 2i x. 2i times x is positive 2i x. And 2i times negative 2i is going to be negative 4i squared. So once I simplify some things, I cancel out my like terms, so I got negative 2ix plus 2ix. I'm going to have x squared minus 4 I squared. And remember, I squared is negative 1. So negative 4 times negative 1 is going to give me plus 4, which means this is x squared plus 4. Awesome. Okay. So yeah, x plus 2i times x minus 2i gave me x squared plus 4. Now I have this part here. And this part is going to be a little bit trickier. So first things first, I got x times x. It's going to give me x squared. I'll do it in a different color just so I can differentiate it from that stuff over there. We'll go with the purple. So I got x squared. And then I have x times negative 2 minus 2 square roots of 2. So minus 2 minus 2 square roots of 2 x. And then I have negative 2 plus 2 square roots of 2 times x. So minus, 2 plus 2 square roots of 2 x. And then I have this here. I have 2 plus 2 square roots of 2 times 2 minus 2 square roots of 2. And to figure this out, I'm actually going to do a little bit of a mini FOIL thing. So let's see. I'm just going to come down here for a second. So I have 2 plus 2 square roots of 2. Because I'm doing this, I'm doing that times that. Times 2 minus 2 square roots of 2. And technically they're both negative because there's a negative in front of both these numbers, but negative times negative is positive, so I'm just going to not worry about the negative. Okay, so I'm going to FOIL these separately now. So I have 2 times 2 is 4. I have 2 times negative 2 square roots of 2 is going to be negative 4 square roots of 2. I have 2 square roots of 2 times 2 is going to be positive 4 square roots of 2. And I have 2 square roots of 2 times 2 square roots of 2. That is going to get me, actually 2 square roots of 2 times negative 2 square roots of 2. Okay, so that's going to get me 4 square roots of 2 squared. And the square root of 2 squared is going to be 2 because the square root and the square cancel out. So this is just the same as 4 times 2, and 4 times 2 is 8. So I am replacing all of this with 8. And these cancel out, so I have negative 4 square roots of 2 plus 4 square roots of 2. Those cancel out. And now I just have 4 minus 8 equals negative 4. Which means that I have all this minus 4. Okay, so I hope you got that because I'm erasing it because I don't have room otherwise. Sorry. Okay, there. So, let's see. What is going on with these negative 2 minus 2 square roots of 2? Let's see. So if I distribute this negative sign, that is going to get me x squared, and also distribute the x. So x squared minus 2x minus 2 square roots of, no, actually it would be plus because it's a negative times a negative. 2 square roots of 2x. And then I'm also going to distribute the negative and the x here. So I have minus 2x minus 2 square roots of 2x minus 4. I combine like terms, so I have x squared, and then I have minus 2x is going to be minus 4x. And then I have plus 2 square roots of 2x minus 2 square roots of 2x. Those cancel out. And ultimately, since those cancel out, that is why we have to take the complex conjugate when there's a root. We always have to take the complex conjugate when there's a root because they'll cancel out and all I'm left with is x squared minus 4x minus 4. And I'm multiplying that times x squared plus 4. Okay, so when I multiply that times x squared plus 4, I'll take it back to blue. So let's see. Yeah, I got x squared plus 4 times x squared minus 4x minus 4. I'm doing x squared times x squared is x to the 4th. I'm doing x squared times negative 4x is negative 4x to the 3rd. I got x squared times negative 4 is negative 4x squared. And then I got 4 times x squared is 4x squared. I got 4 times 4x, or 4 times negative 4x, is going to be negative 16x. And I got 4 times negative 4 is going to be negative 16. So once I combine everything in this polynomial, I have the negative 4x squared plus 4x squared. So, those two just cancel out. And all I'm left with is this. The polynomial is going to be x to the 4th minus 4x to the 3rd minus 16x minus 16. And that polynomial has the roots negative 2i, 2 plus 2 square roots of 2, 2i, and 2 minus 2 square roots of 2. And this is a nice polynomial. If you look at that, you would think, oh, that'll be pretty simple. I shouldn't have problems factoring that. But, you'd be thinking wrong because it's going to have some pretty messy factors. But that's okay because it's a nice polynomial regardless. So this is what I basically want you guys to finish this worksheet, other than, like I said, skip 13 and 14. And I do know that this is hard stuff. You do have to do these mini foiling, and it does take multiple steps to get the polynomial. But I know you guys can do it. I've seen the work you've been putting in the past couple of weeks. I really do appreciate you guys. I appreciate the online learning you've been doing. I know it's difficult, and I'm just really proud of you guys. So keep it up. Thank you. And yeah, complete this worksheet. I will post it along with the video.